In 1994, astronomers detected something moving faster than light, not approximately the speed of light, not close to the speed of light in a way that rounds up to something technically imprecise. Faster, 6 times faster. A jet of plasma erupting from a black hole in M87, the same galaxy whose central black hole was famously imaged in 2019, appearing to travel at 6 times the speed of light across the sky. The measurement was real, the object was real, the motion was real, and it violated the most fundamental constraint in physics, the cosmic speed limit established by Einstein's special theory of relativity in 1905, confirmed by every experiment ever designed to test it, built into the foundations of every technology, from GPS satellites to particle accelerators to the nuclear reactions that power stars. Nothing can travel faster than light, except this jet appeared to. For a brief period in 1994, before the explanation was worked out and confirmed, the detection sat in the data as an anomaly that had no obvious resolution, an observation that, taken at face value, described something physically impossible. The resolution, when it came, was not a discovery that special relativity was wrong. It was something stranger and more interesting, a geometric illusion so precisely constructed by the mechanics of space-time and the geometry of high-velocity motion that it could fool the most sophisticated instruments astronomers had ever built into reporting the impossible as real. Understanding how this illusion works requires understanding what happens to space and time when something moves at a significant fraction of the speed of light. And understanding that reveals something about the universe that is, in its own way, as strange as the faster-than-light motion that turned out to be an illusion. Start with M87. M87 is an enormous elliptical galaxy, approximately 55 million light-years from Earth, located in the Virgo cluster, one of the closest large galaxy clusters to the Milky Way. At its center sits one of the most massive black holes known, 6.5 billion times the mass of our Sun. The 2019 image published by the Event Horizon Telescope collaboration, the first direct image of a black hole's shadow, was an image of this object. From the region surrounding M87's central black hole, an astrophysical jet extends outward for approximately 5,000 light-years. Jets are common features of active galactic nuclei, supermassive black holes that are actively accreting material from an accretion disk and, through a mechanism not yet fully understood, launching twin beams of plasma and magnetic field perpendicular to the disk at close to the speed of light. M87's jet was first detected in 1918 by astronomer Heber Curtis, who observed a curious straight ray extending from the galaxy's nucleus. For decades, it was an observed but poorly understood feature. By the 1990s, radio telescope observations had resolved the jet's structure in detail and began measuring the apparent motion of bright knots within it. The knots were moving at 6 times the speed of light. The phenomenon is called superluminal motion. It has been detected not just in M87, but in dozens of sources: radio galaxies, quasars, blazars, gamma-ray burst afterglows, and even within our own galaxy in objects called microquasars. It is not a rare anomaly, but a regularly observed feature of relativistic jets in the universe, and every case is explained by the same geometric effect.
Here is how it works. Imagine a jet of plasma traveling toward you at 95% of the speed of light. Not directly toward you, at an angle. The jet is pointed mostly in your direction, but slightly off-axis, making a small angle with your line of sight. The plasma in the jet emits light continuously. As it moves toward you, each successive burst of light it emits has a shorter distance to travel than the previous burst because the jet itself has moved closer to you between emissions. The light is being compressed in time. Pulses that were emitted at intervals of, say, 1 year arrive at your detector at intervals considerably shorter than 1 year because the jet was chasing its own light. This is the Doppler effect in its relativistic form. When the jet is pointed toward you, the time between light pulses arriving at your detector is shorter than the time between their emission. The light you receive appears to arrive more frequently than it was sent. Now, watch how this affects the apparent position of the plasma as seen from Earth. The jet emits a burst of light from position A. A year later, it emits another burst from position B, which is close to position A in your line of sight direction, but has moved sideways, perpendicular to your line of sight, by some distance. The burst from position B arrives at Earth almost at the same time as the burst from A, because the jet has been moving toward you, and the light from B has a much shorter distance to travel than the light from A. The result, you detect the jet at position A, and almost immediately, in a very short time interval, you detect it at position B. The sideways distance between A and B, divided by the very short time interval between the detections, gives you an apparent transverse velocity. That apparent transverse velocity can exceed the speed of light. Not because anything moved faster than light, because you are dividing a real transverse distance by an artificially compressed time interval. A compression produced by the jet chasing its own light as it moves toward you. The faster-than-light motion is a projection artifact, a consequence of geometry and the finite speed of light. Real motion below the speed of light, producing an apparent motion above it. The mathematics confirms this completely. For a jet moving at velocity v at angle theta to the line of sight, the apparent transverse velocity as observed from Earth is v apparent equals v sine theta over 1 minus v over c cosine theta. When the geometry is right, when the jet is moving at close to the speed of light and pointing nearly but not quite directly at the observer, the denominator of this expression becomes very small, and the apparent velocity becomes very large. For M87's jet, moving at approximately 99% of the speed of light and oriented at approximately 19 degrees to our line of sight, the formula gives an apparent transverse velocity of approximately 6 times the speed of light, exactly what was measured. Not a violation of special relativity, a confirmation of it. The superluminal motion of M87's jet is precisely predicted by the mathematics of special relativity, applied to an object moving at relativistic velocities toward an observer. Einstein's equations do not forbid the observation of apparent faster-than-light motion. They forbid actual faster-than-light motion of anything with mass. The jet's plasma never exceeded the speed of light. Its apparent velocity, as calculated from measurements made 60 million light-years away on a timescale compressed by relativistic geometry, exceeded it in a precisely calculable way. But this answer, satisfying as it is, raises the question of what a jet moving at 99% of the speed of light actually is, because that is extraordinary in its own right. The mechanism by which astrophysical jets are accelerated to near-light speeds is not fully understood. The leading framework involves the interaction of the black hole's spin with the magnetic field of the accretion disk, the Blandford-Znayak mechanism, proposed in 1977, in which the rotational energy of the black hole itself is extracted through magnetic field lines threaded through the ergosphere and converted into the kinetic energy of the jet. The black hole is a rotational engine. Material falling into it spins up the black hole. The spinning black hole twists the surrounding magnetic field. The twisted field accelerates plasma along the rotation axis. The plasma is flung outward at a significant fraction of the speed of light. This is an extraordinarily efficient process. M87's jet carries power estimated at approximately 10 to the 44th watts, comparable to the luminosity of the entire galaxy. This power comes from the rotation of a black hole that has been spinning for billions of years, continuously extracting rotational energy and converting it into the kinetic energy of plasma moving at close to the speed of light. The fastest natural accelerator in the observable universe is a spinning black hole, and its product, the jet of plasma it launches, is so fast that watching it from 60 million light-years away in the compressed geometry of relativistic observation makes it appear to violate the most fundamental law of physics.
M87 is the most famous case, but it is far from the only one. Within our own galaxy, there are objects called microquasars, binary systems in which a stellar mass black hole or neutron star accretes material from a companion star and launches jets. These jets are smaller and less powerful than the jets of active galactic nuclei, but they operate on similar physical principles. The microquasar GRS 1915+105, discovered in 1992, shows apparent superluminal motion in its jets. Bright knots of plasma appeared to move outward from the central object at approximately 1.5 times the speed of light, an apparent superluminal velocity produced by the same geometric effect as M87, but at a source only a few tens of thousands of light-years away, rather than millions. This object was briefly the most controversial thing in astrophysics, a galactic source, something in our own Milky Way, not some distant quasar, appearing to produce superluminal motion. The implications, before the geometric explanation was confirmed for this specific case, were considerable. The geometric explanation held here too. The jets of GRS 1915+105, moving at approximately 98% of the speed of light, produce apparent superluminal velocities through exactly the same mechanism as M87. Now here is where the story takes its second turn. Superluminal motion is not the only way the universe appears to violate the speed limit. The expansion of the universe itself is faster than light. Galaxies beyond a certain distance, approximately 14 billion light-years, the Hubble radius, are receding from us faster than the speed of light, not because they are moving through space at superluminal velocities, because the space between us and them is expanding. The expansion of space itself is not limited by special relativity's speed limit, which applies to motion through space, not to the expansion of space. The result is that there are regions of the universe, regions that existed within our observable sphere in the past, that are now receding faster than light can cross the expanding gap between us and them. Light they emit today will never reach us. They have crossed the cosmological horizon. This is not apparent motion caused by geometric compression. This is real recession velocity exceeding the speed of light, caused by the expansion of space itself. And it means that the observable universe, the sphere of space from which light has reached us, is not the same as the reachable universe. Even if you could travel at the speed of light, you could not reach the galaxies currently receding faster than light from us. The expanding space would defeat you. The universe permits faster-than-light recession through expansion. It forbids faster-than-light motion through space. The distinction is precise, mathematical, and has profound consequences for what is and is not accessible from any point in the cosmos. There is a third phenomenon that superficially resembles faster-than-light motion and has generated headlines over the years: quantum entanglement. Two particles can be entangled, connected in a quantum mechanical way, such that measuring a property of one instantly determines the corresponding property of the other, regardless of the distance between them. Perform a measurement on one particle in a laboratory. The corresponding particle, which might be on the other side of the galaxy, instantaneously assumes a definite state, instantaneously, across arbitrary distances, faster than light could cross the distance between the particles. This seems to violate special relativity, but it does not. The key is that the correlation between the particles cannot be used to transmit information faster than light. The outcome of measuring one particle is random. You cannot control which result you get. The distant particle assumes a correlated state, but you cannot know what state it assumed without receiving that information through classical channels, which travel at or below the speed of light. Entanglement is real. The correlations are real. They are instantaneous across arbitrary distances, but they carry no information because neither party can control or predict the outcome of their measurement. Special relativity is not violated. The apparent instantaneous connection is real, but causally inert. The universe allows quantum correlations to be instantaneous. It forbids those correlations from being used as a channel for faster-than-light signaling. What emerges from all of this, from superluminal jets and expanding space and quantum entanglement, is a picture of the universe that is simultaneously more constrained and more strange than simple intuition suggests. More constrained because the speed of light as a limit to the transmission of information and the motion of matter through space appears to be absolute. Every apparent violation has an explanation that preserves the limit. Every test that has ever been performed confirms it. No signal, no object, no physical process has ever been shown to transmit information faster than light through space. Stranger because the universe routinely produces phenomena that look like faster-than-light motion, jets of plasma that appear to exceed c, galaxies that recede faster than c, quantum correlations that are instantaneous across arbitrary distances, all of which are real phenomena that do not violate the limit but that require careful analysis to explain. The universe is not simple. The speed limit is not obvious from observation. It requires understanding the geometry of space-time, the mathematics of relativity, the distinction between motion through space and expansion of space, and the difference between quantum correlation and information transmission. In 1994, something appeared to move at 6 times the speed of light. The explanation required invoking special relativity, the same theory that establishes the speed of light as a limit, to show precisely how an object moving at 99% of the speed of light, pointed nearly but not quite directly at us from 60 million light-years away, would appear to move at 6 times that speed. The law was not broken. The law was what produced the illusion of the law being broken. That is not a paradox. It is the universe operating exactly as Einstein described, with a geometry so precise and so consistent that even its apparent violations are predicted by the same mathematics that establishes the rules. A black hole in the center of a galaxy, spinning, launching plasma at near light speeds, the plasma chasing its own light across millions of light-years, the light arriving at Earth in a compressed time sequence that makes the impossible look real. And a species on a small planet building telescopes and doing mathematics and eventually understanding not just what they were seeing, but why the impossible was not impossible, why the universe's deepest law was not broken, but was in fact the explanation for everything. The speed of light is the limit. The universe uses that limit to produce the appearance of something beyond it, and in the gap between appearance and reality, in the precise, predictable, mathematically beautiful gap, physics lives.